Before the 20th century, physics was built on an extraordinary sense of confidence. For centuries, the natural world had appeared orderly, predictable, and obedient to precise laws. From the motion of falling objects to the paths of planets across the sky, everything seemed to follow rules that could be written down, calculated, and trusted. This confidence did not emerge overnight. It was the result of a long intellectual journey that began with ancient philosophers and reached its peak with the triumphs of classical physics in the 17th, 18th, and 19th centuries. By the time Werner Heisenberg was born, the scientific community largely believed that the fundamental structure of reality had already been understood. What remained, many thought, was simply to refine measurements and calculate details with greater accuracy. At the heart of this certainty stood Isaac Newton. His laws of motion and universal gravitation provided a powerful framework that explained both everyday experiences and the grand movements of the cosmos. A stone thrown into the air, the swing of a pendulum, the tides of the oceans, and the orbit of the moon could all be described using the same mathematical principles. This unification created a deep sense of trust in the idea that nature was governed by fixed, unchanging laws. If the position and velocity of an object were known at a given moment, its future behavior could be predicted exactly. The universe appeared to function like a perfectly constructed clock, ticking forward with mechanical precision. This deterministic view of nature shaped not only science but also philosophy and culture. Thinkers began to imagine a universe in which nothing happened by chance. Every event was seen as the inevitable result of previous conditions. The famous idea associated with Pierre Simon Laplace captured this mindset perfectly. Laplace proposed that if an intellect existed that knew the position and motion of every particle in the universe at a single instant, it could calculate the entire future and reconstruct the entire past. In such a universe, uncertainty had no fundamental role. Ignorance was merely temporary, a sign that measurements were incomplete or calculations insufficient. Throughout the 19th century, this worldview seemed only to grow stronger. Classical mechanics was joined by other powerful theories that reinforced the sense of certainty. James Clerk Maxwell unified electricity, magnetism, and light into a single elegant theory. His equations described electromagnetic waves with stunning accuracy and predicted that light itself was an electromagnetic phenomenon. These equations worked so well that many physicists believed they represented a final, almost perfect description of physical reality. The success of thermodynamics and statistical mechanics further strengthened confidence, even when probability entered the picture. Probability, in this context, was not seen as fundamental uncertainty, but as a practical tool for dealing with large numbers of particles whose individual motions were too complex to track. By the late 19th century, physics had achieved remarkable success. Industrial technology flourished as scientific principles were applied to engines, bridges, communication systems, and manufacturing. Telegraph wires carried messages across continents. Steam engines powered factories and transportation. Precision instruments allowed scientists to measure time, distance, and energy with unprecedented accuracy. The close relationship between theory and experiment created a powerful feedback loop. Theories guided experiments, and experiments confirmed theories. This harmony reinforced the belief that science was steadily approaching a complete and final understanding of nature. Yet beneath this surface of confidence, subtle cracks were beginning to appear. Some experimental results did not fit neatly into existing theories. The behavior of heated objects emitting light, known as blackbody radiation, resisted explanation by classical physics. According to established theory, objects should emit infinite energy at certain wavelengths, a prediction that clearly contradicted reality. This problem was initially seen as a technical issue, not a sign of a deeper crisis. Many physicists believed it would be resolved with minor adjustments, without challenging the foundations of classical theory. Similarly, experiments involving the photoelectric effect revealed puzzling behavior. Light shining on certain metals caused electrons to be ejected, but the energy of those electrons depended on the frequency of the light, not its intensity. This contradicted the wave theory of light, which had been so successful under Maxwell's framework. Once again, these anomalies were viewed as isolated puzzles rather than indications of a fundamental shift. The prevailing attitude was that classical physics was essentially complete, and that remaining problems were small clouds on an otherwise clear horizon. This confidence was famously expressed by physicist Albert Michelson, who suggested that future discoveries would involve adding decimal places to existing measurements rather than discovering entirely new principles. Such statements reflected a widespread belief that the core structure of physics was finished. Young students entering the field were often encouraged to pursue engineering or applied science, as theoretical physics seemed to offer little room for groundbreaking discoveries. The belief in certainty also shaped how scientists thought about observation and measurement. In classical physics, measuring an object was assumed to reveal properties that already existed independently of the observer. The act of measurement did not alter the system in any fundamental way. A thermometer measured temperature without changing it. A ruler measured length without affecting the object. This assumption reinforced the idea that reality was objective, stable, and fully accessible to human inquiry. Time itself was treated as absolute. According to Newtonian physics, time flowed uniformly everywhere in the universe, independent of motion or observation. Space was a fixed stage on which events unfolded, unaffected by the presence of matter or energy. These assumptions created a clear and intuitive picture of reality that aligned closely with everyday experience. They also contributed to the sense that the universe was fundamentally knowable in a complete and final way. Education and scientific training reflected this worldview. Students learned physics as a collection of well-established laws, derived from first principles and confirmed by experiment. Problem-solving focused on applying formulas to calculate precise outcomes. Uncertainty was treated as experimental error, something to be minimized through better instruments and techniques. The idea that uncertainty might be intrinsic to nature itself was almost unthinkable. Philosophically, this era was marked by strong confidence in rationalism and human reason. The success of physics supported the belief that the universe was comprehensible and that human intellect was capable of uncovering its deepest secrets. Science was often seen as the ultimate path to truth, surpassing tradition, religion, and speculation. This confidence extended beyond physics into broader cultural attitudes about progress, control, and mastery over nature. Yet as the 19th century gave way to the 20th, the accumulation of unexplained phenomena could no longer be ignored. New experiments probed deeper into the structure of matter, revealing atoms and subatomic particles whose behavior defied classical intuition. Electrons did not behave like tiny billiard balls following predictable paths. Instead, they exhibited strange patterns, sometimes acting like particles and sometimes like waves. Attempts to force these observations into the classical framework led to contradictions and confusion. The discovery of the atom itself marked a turning point. Once thought to be indivisible, atoms were found to contain internal structure, with electrons orbiting a dense nucleus. Classical physics predicted that these electrons should radiate energy continuously and spiral into the nucleus, causing atoms to collapse. Clearly, this did not happen. Matter was stable, and classical theory could not explain why. This failure struck at the heart of the deterministic worldview. Despite these challenges, many physicists still hoped that deeper understanding would restore certainty. They believed that hidden variables or more refined theories would eventually reconcile the anomalies with classical principles. The idea that nature itself might be fundamentally uncertain was resisted because it contradicted centuries of scientific success and philosophical belief. This was the intellectual landscape into which Werner Heisenberg would eventually step. He inherited a tradition of immense confidence, mathematical elegance, and philosophical certainty. At the same time, he faced a growing list of experimental facts that refused to fit within that tradition. The tension between these two forces defined the crisis of early 20th century physics. The world before uncertainty was not ignorant or naive, it was extraordinarily successful, powerful, and convincing. Precisely because of that success, the realization that certainty might be impossible would prove so shocking, transformative, and difficult to accept. In this world, certainty was not merely an assumption, it was the foundation upon which science, technology, and even modern culture were built. To question it was to question the very meaning of scientific knowledge. Yet the stage was already set. The cracks in the classical picture were widening, and the tools developed to describe certainty were beginning to reveal their own limitations. The universe, once seen as a perfectly predictable machine, was quietly preparing to reveal a deeper, stranger reality, one in which certainty would no longer reign supreme. As experiments pushed deeper into the structure of matter, the confidence inherited from classical physics began to face pressures that could no longer be dismissed as minor inconsistencies. Laboratories across Europe were producing results that resisted explanation, and the gap between theory and observation slowly widened. What made this period especially unsettling was that the same mathematical tools and conceptual frameworks that had worked so brilliantly at larger scales failed completely when applied to atoms and radiation. The certainty that once felt unshakable started to show signs of strain, even if many physicists were reluctant to admit it openly. One of the most disturbing aspects of this crisis was that it did not come from a single failure, but from many small, interconnected problems. Each anomaly on its own could be rationalized or temporarily ignored, but together they formed a pattern that hinted at something fundamentally wrong. The classical picture assumed that nature was continuous, smooth, and deterministic. Energy could vary gradually, positions and velocities could be specified with arbitrary precision, and causes always produced predictable effects. Yet experiments increasingly suggested that at microscopic scales, nature behaved in abrupt, discontinuous, and deeply counterintuitive ways. The idea of quantization was among the first serious blows to classical certainty. When Max Planck introduced the concept that energy could be emitted or absorbed only in discrete packets, he did so reluctantly. Planck himself did not believe he was overturning the foundations of physics. He viewed his solution to the blackbody radiation problem as a mathematical trick, a temporary measure to make equations match experimental data. Yet this trick carried revolutionary implications. If energy itself was quantized, then the smooth, continuous world imagined by classical physics did not exist at the most fundamental level. Soon after, Albert Einstein extended this unsettling idea by proposing that light itself was composed of quanta, later called photons. This explanation successfully accounted for the photoelectric effect, but it came at a high conceptual cost. Light, long understood as a wave spreading smoothly through space, now appeared to behave like a stream of particles under certain conditions. The wave-particle duality shattered the clear categories upon which classical thinking depended. Something could no longer be neatly classified as either a wave or a particle. It could be both, depending on how it was observed. These developments forced physicists to confront an uncomfortable realization. Their theories were no longer describing an objective reality independent of observation in the way they once had. Instead, the results of experiments seemed to depend on the experimental setup itself. How one chose to measure a system influenced what could be known about it. This was a profound departure from the classical assumption that measurement merely revealed pre-existing properties. As atomic models developed, the crisis deepened. Early planetary models of the atom borrowed heavily from classical mechanics, picturing electrons orbiting the nucleus like planets around the sun. While visually appealing, these models quickly ran into fatal problems. According to classical electrodynamics, orbiting electrons should continuously lose energy and collapse into the nucleus. Matter, as a stable structure, should not exist, yet it clearly did. The stability of atoms stood as undeniable evidence that classical physics was missing something essential. Niels Bohr attempted to address this by introducing quantized orbits, allowing electrons to occupy only specific energy levels. While Bohr's model successfully explained certain spectral lines, it did so by imposing rules that had no grounding in classical reasoning. Electrons were allowed to jump between orbits without traveling through the space in between, emitting or absorbing energy in discrete amounts. These jumps defied intuition and undermined the idea of smooth, continuous motion. Bohr's model worked, but it raised more philosophical questions than it answered. At the same time, experimental techniques were becoming more refined. New instruments allowed scientists to probe smaller distances and shorter timescales. Ironically, the more precise the instruments became, the more elusive certainties seemed to be. Efforts to measure the behavior of electrons revealed that attempting to pin down one property often disturbed another. This was initially interpreted as a technical limitation, something that could be overcome with better equipment. Yet repeated experiments suggested that the disturbance was not accidental, but unavoidable. The growing role of probability further unsettled classical thinking. In statistical mechanics, probability had been used as a practical tool, a way to describe the behavior of large numbers of particles whose individual motions were too complex to track. But at the atomic level, probability appeared to be fundamental. Even when conditions were carefully controlled, outcomes could not be predicted with certainty, only with probabilities. This was not ignorance due to lack of information, it seemed to be an intrinsic feature of nature. This shift challenged deeply held philosophical assumptions. Determinism had been more than a scientific principle, it was a worldview. It suggested that the universe was fully governed by cause and effect, leaving no room for genuine randomness. Human understanding, in principle, could achieve complete knowledge of the natural world. The emerging quantum phenomena threatened this belief. If nature itself was probabilistic, then complete prediction was impossible, not because of human limitations, but because of how reality was structured. Many physicists resisted this implication. They searched for hidden variables, unseen mechanisms that might restore determinism beneath the apparent randomness. The hope was that quantum behavior was merely a sign of incomplete theory, and that a deeper, more comprehensive framework would eventually reestablish certainty. This resistance was understandable. To accept fundamental uncertainty was to abandon a vision of science that had guided progress for centuries. The tension between classical certainty and quantum mystery created an atmosphere of intense intellectual struggle. Conferences and informal discussions became arenas for debate, disagreement, and creative speculation. Young physicists were entering a field in turmoil where established authorities disagreed sharply and basic concepts were up for revision. It was no longer clear what constituted a satisfactory explanation. Mathematical success no longer guaranteed conceptual clarity. This period also revealed the limits of human intuition. Classical physics aligned closely with everyday experience. Objects moved smoothly, causes produced predictable effects, and measurements felt straightforward. Quantum phenomena, by contrast, defied common sense. Particles appeared to exist in multiple states at once, waves collapsed into particles upon observation, and outcomes could not be predicted with certainty even in principle. The human mind, shaped by macroscopic experience, struggled to grasp these ideas. The language of physics itself began to change. Terms like trajectory, position, and velocity, which had clear meanings in classical mechanics, became ambiguous at microscopic scales. New mathematical formalisms emerged that prioritized calculation over visualization. Equations no longer described objects moving through space in familiar ways, but relationships between abstract quantities and probabilities. This shift marked a departure from the comforting clarity of classical descriptions. Despite the confusion, the experimental evidence was undeniable. Nature was speaking in a new language, and classical physics could no longer translate it accurately. The old framework had reached its limits. What was once considered the ultimate expression of certainty now appeared incomplete, even misleading, when applied to the smallest scales of reality. It is important to recognize that this collapse of certainty was not a failure of science, but a consequence of its success. The very precision and rigor that made classical physics powerful also revealed its boundaries. By pushing inquiry further and measuring nature more deeply, scientists uncovered layers of reality that classical concepts were never designed to handle. Certainty did not disappear because science was weak, but because it was strong enough to expose its own limitations. This intellectual environment set the stage for a radical rethinking of physics. The crisis demanded new ideas, new mathematical tools, and new philosophical attitudes. It required a willingness to let go of comforting assumptions and accept that the universe might not conform to human expectations of order and predictability. It was within this charged atmosphere that Werner Heisenberg would make his decisive contribution. Heisenberg's work did not emerge in isolation. It was shaped by this broader struggle between an old worldview and a new, unsettling reality. The collapse of classical certainty was already underway, even if its full implications were not yet understood. What Heisenberg would do was to bring this uncertainty into sharp focus, revealing it not as a temporary problem to be solved, but as a fundamental feature of the universe itself. Thus, the world before uncertainty was not simply replaced overnight. It resisted, adapted, and struggled against the new evidence. But step by step, experiment by experiment, the foundations of classical certainty eroded. By the time Heisenberg introduced his revolutionary ideas, the ground was already unstable. The belief in a fully predictable universe had been weakened, preparing physics for a transformation that would forever change humanity's understanding of reality. Werner Heisenberg's early life unfolded during one of the most turbulent periods in modern European history, and this environment played a decisive role in shaping both his intellect and his character. Born in 1901 in Würzburg, Germany, Heisenberg entered the world at a moment when old certainties, political, cultural, and scientific, were already beginning to fracture. His childhood and adolescence were marked by war, social upheaval, and a deep questioning of authority and tradition. These experiences did not merely surround him, they entered into his thinking and influenced the way he would later approach the deepest problems of physics. Heisenberg grew up in an academically rich household. His father was a professor of classical philology, deeply immersed in the study of ancient Greek texts. From an early age, Werner was exposed to rigorous intellectual discipline, precision of language, and respect for abstract thought. This background trained his mind to appreciate structure, logic, and the power of symbols, skills that would later prove invaluable in his work on quantum mechanics. Yet his upbringing was not limited to books and scholarship. He was also deeply engaged with music, particularly piano, which cultivated in him a sensitivity to patterns, harmony, and emotional expression beyond words. The outbreak of the First World War shattered the relative stability of Heisenberg's early childhood. Germany, like much of Europe, was thrown into chaos, scarcity, and ideological conflict. As a young boy, Heisenberg witnessed the collapse of an old order that had seemed permanent. Authority figures lost credibility, institutions faltered, and the future appeared uncertain. This environment left a lasting impression on him. It taught him that systems believed to be stable could fail, and that certainty, whether political or intellectual, was fragile. These lessons would later echo in his scientific thinking, even if he did not consciously recognize the connection at the time. During the war and its aftermath, Heisenberg became involved in youth movements that emphasized self-discipline, communal responsibility, and personal development. These groups often met in nature, engaging in long hikes, discussions, and physical challenges. Such experiences fostered resilience and independence. Heisenberg learned to think for himself, to question received wisdom, and to rely on inner conviction rather than external approval. This independence would become a defining feature of his scientific career, enabling him to pursue unconventional ideas even when they conflicted with established authorities. The intellectual climate of post-war Germany was one of deep uncertainty and intense creativity. Traditional values were being reassessed, and new ideas were emerging in art, philosophy, and science. Heisenberg entered university at a time when physics itself was undergoing a profound identity crisis. Classical theories that had once seemed unassailable were increasingly unable to explain experimental results. For a young student with a sharp mind and a willingness to challenge assumptions, this instability was not discouraging, but stimulating. It offered an opportunity to participate in the reconstruction of knowledge itself. Heisenberg studied physics in Munich under Arnold Sommerfeld, one of the most influential theoretical physicists of the time. Sommerfeld was known for his openness to new ideas and his encouragement of independent thinking. Under his guidance, Heisenberg developed exceptional mathematical skills and learned to approach physical problems with both rigor and creativity. Sommerfeld did not demand blind adherence to established theories. Instead, he emphasized the importance of confronting experimental facts honestly, even when they conflicted with existing models. At the same time, Heisenberg was deeply influenced by philosophical questions about the nature of knowledge and reality. He was not content to simply manipulate equations. He wanted to understand what physical theories meant, what they said about the world, and what their limitations were. This philosophical curiosity distinguished him from many of his peers. While others focused on refining calculations within known frameworks, Heisenberg was willing to question the frameworks themselves. The challenges facing physics during Heisenberg's student years were profound. Atomic spectra revealed discrete lines that classical theory could not explain. The behavior of electrons defied intuitive description. Attempts to visualize atomic processes using familiar concepts repeatedly failed. For many students, this confusion was frustrating. For Heisenberg, it was an invitation. He sensed that the difficulty lay not in the mathematics, but in the assumptions underlying the theories. Something fundamental needed to change. Heisenberg's personal temperament also played a crucial role. He was intensely focused, sometimes to the point of isolation. When working on a problem, he could withdraw from social life entirely, devoting all his energy to understanding a single question. This intensity allowed him to pursue ideas that others abandoned as too difficult or too abstract. At the same time, he was capable of great humility before nature, recognizing that human intuition might not be the ultimate guide to understanding reality. His early research exposed him to the limitations of visual models in atomic physics. Many physicists still tried to imagine electrons moving along definite paths, similar to planets orbiting the sun. Heisenberg grew increasingly skeptical of such images. He noticed that these pictures often contradicted experimental results and relied on unobservable assumptions. This skepticism was not merely technical, it reflected a deeper philosophical stance shaped by his upbringing in a world where familiar structures had repeatedly failed. Heisenberg's curiosity drove him to ask a radical question: what if physics should concern itself only with quantities that can be observed and measured? This idea did not arise suddenly, but developed gradually as he struggled with the inconsistencies of existing atomic models. His willingness to consider such a departure from tradition was rooted in his formative experiences. Having lived through social and political collapse, he was less attached to inherited certainties. He understood, at a deep level, that clinging to outdated frameworks could hinder progress. The psychological pressure of working in a field without clear foundations was immense. Young physicists like Heisenberg faced the challenge of contributing to a discipline where even basic concepts were under dispute. Yet this uncertainty also created a unique freedom. Without a fixed roadmap, creative thinking became not just possible but necessary. Heisenberg thrived in this environment. His curiosity was sharpened by the sense that he was exploring unknown territory, where bold ideas were required. Heisenberg's early encounters with other leading physicists further shaped his development. Interactions with figures such as Niels Bohr exposed him to different ways of thinking about quantum problems. Bohr's emphasis on complementarity and the limits of classical language resonated with Heisenberg's own doubts about visualization and certainty. These intellectual exchanges reinforced his sense that physics was entering a new phase, one that demanded both mathematical innovation and philosophical reflection. Crucially, Heisenberg did not view uncertainty as a weakness. From his earliest years, he had learned to live with instability, whether social, political, or intellectual. This comfort with uncertainty allowed him to approach unsolved problems without fear. While others sought to restore classical certainty, Heisenberg was open to the possibility that nature itself might resist complete description. This openness was not pessimistic. It was deeply realistic. His formative years thus created a unique blend of traits: mathematical rigor, philosophical depth, intellectual independence, and emotional resilience. These qualities did not guarantee success, but they prepared him to recognize revolutionary ideas when they appeared. Heisenberg's curiosity was not satisfied with incremental improvements. It sought fundamental understanding. His mind had been shaped by crisis, but instead of being paralyzed by it, he learned to see crisis as a source of insight. By the time Heisenberg began his most important work, he was already primed for radical innovation. He had grown up watching certainties collapse and new structures struggle to emerge. He had learned that progress often requires abandoning familiar ground. This personal history, combined with the scientific crisis of early 20th century physics, positioned him uniquely to make a contribution that would redefine the limits of knowledge itself. In this sense, Heisenberg's youth was not merely a prelude to his scientific achievements, it was an essential part of them. The uncertainty he would later formalize in mathematical terms was something he had already encountered in life. His curiosity was sharpened by instability, and his willingness to question certainty was rooted in experience. The young mind shaped by crisis would eventually reveal to the world that uncertainty was not a temporary problem to be solved, but a fundamental feature of reality. As Heisenberg moved deeper into his academic life, the tension between inherited knowledge and emerging questions became more intense. University education exposed him to the most advanced physics of the time, yet it also made the shortcomings of that physics impossible to ignore. Lectures presented elegant theories, but laboratory results whispered contradictions. For Heisenberg, this gap was not a sign of confusion to be avoided. It was a signal pointing toward deeper truth. He began to understand that the crisis in physics was not accidental but inevitable, the result of pushing human understanding to its limits. The intellectual atmosphere surrounding Heisenberg was unusually rich. Germany, despite its political instability, was a center of scientific innovation. Seminars were vibrant, debates were sharp, and disagreement was not only tolerated but encouraged. Young physicists were expected to defend their ideas rigorously, even against established authorities. This environment strengthened Heisenberg's confidence in his own reasoning. He learned that respect in science was earned not through obedience, but through clarity of thought and honesty toward experimental facts. At the same time, Heisenberg's personal discipline intensified. He adopted a lifestyle marked by long periods of concentration, physical activity, and solitude. Hiking in the mountains became a recurring theme in his life, offering both physical endurance and mental clarity. These solitary moments allowed him to reflect deeply on abstract problems, free from distraction. Nature, with its vastness and order, provided a contrast to the confusing behavior of the atomic world he was trying to understand. This contrast sharpened his awareness that intuition drawn from everyday experience might not apply at the smallest scales of reality. As his studies progressed, Heisenberg became increasingly dissatisfied with the way atomic theory relied on visual metaphors. Diagrams of electrons orbiting nuclei seemed comforting, but they explained little. He noticed that such images often survived not because they were accurate, but because they were familiar. This realization reinforced his skepticism toward any explanation that depended too heavily on imagination rather than measurable results. He began to suspect that the true structure of atomic reality might be fundamentally non-visual, accessible only through abstract relationships expressed mathematically. This shift in attitude marked a critical stage in Heisenberg's intellectual development. Many physicists of the time believed that a good theory should provide a clear picture of what was happening in nature. Heisenberg began to question this requirement itself. What if nature did not offer a picture in human terms? What if demanding visual clarity was an obstacle rather than a virtue? These questions reflected a maturity that went beyond technical skill. They revealed a philosopher's mindset emerging within a physicist. His interactions with mentors and peers further reinforced this transformation. Conversations were not limited to calculations. They extended into discussions about meaning, interpretation, and the role of the observer. Heisenberg listened carefully, absorbing different perspectives, but he was never content to accept conclusions without internal coherence. He valued consistency between theory and experience, even if achieving that consistency required abandoning long-held assumptions. The emotional dimension of this period should not be underestimated. Working at the edge of knowledge is psychologically demanding. The absence of clear answers can create doubt and frustration. Heisenberg experienced these pressures intensely. There were moments of confusion, self-questioning, and intellectual isolation. Yet instead of retreating to safer problems, he pushed forward. He seemed driven by a conviction that clarity would eventually emerge, not by restoring old ideas, but by discovering new ones. Heisenberg's growing awareness of limits became central to his thinking. He saw that every theory operates within a domain where its concepts make sense. Outside that domain, those same concepts can mislead. This insight applied not only to physics, but to human knowledge in general. It suggested that understanding reality requires humility, an acceptance that no single framework can capture everything. This attitude distinguished Heisenberg from those who sought final answers. He was increasingly comfortable with provisional truths. The political and cultural instability of Germany continued to shape his worldview. Economic hardship, social unrest, and ideological conflict created a backdrop of uncertainty that mirrored the situation in physics. Institutions that once appeared solid were being questioned, reformed, or dismantled. For Heisenberg, this parallel reinforced the idea that certainty is often an illusion maintained by habit rather than evidence. Both society and science, he observed, must adapt or risk stagnation. As he completed his early academic milestones, Heisenberg emerged as a physicist who was technically brilliant yet unusually reflective. He did not see mathematics as an end in itself, but as a language capable of expressing relationships that defied classical imagery. He recognized that the crisis in physics demanded courage as much as intelligence. To move forward, one had to accept the possibility that reality might be stranger than previously imagined. This acceptance did not come easily. It required letting go of the comfort provided by deterministic explanations. It meant embracing probability not as a temporary substitute for ignorance, but as a fundamental aspect of how nature behaves. For Heisenberg, this shift was gradual, shaped by years of exposure to instability, contradiction, and unresolved questions. His life experiences had prepared him for this intellectual leap, even before he articulated it scientifically. The seeds planted during his youth were now beginning to bear fruit. His comfort with uncertainty, his skepticism toward unquestioned authority, and his willingness to rethink basic concepts all converged. Heisenberg was no longer simply learning physics, he was preparing to redefine it. The collapse of certainty he had witnessed in society and culture found a striking parallel in the collapse of certainty within science itself. By the time Heisenberg stood on the threshold of his most important work, his mindset was uniquely suited to the task. He was not searching for a return to the old order, nor was he driven by rebellion for its own sake. He sought coherence, even if that coherence required accepting limits on what could be known. His journey from a childhood shaped by crisis to a scientific career defined by questioning certainty reveals a profound continuity. The same forces that unsettled the world around him also sharpened his insight into the nature of reality. This formative period was essential in shaping the scientist who would later challenge the deepest assumptions of physics. Heisenberg did not arrive at his revolutionary ideas by accident. They emerged from a life lived in the shadow of uncertainty, where stability could never be taken for granted. His curiosity was fueled by disruption, his discipline forged by challenge, and his philosophy shaped by the recognition that certainty, whether in life or in science, is often far more fragile than it appears. In this way, the young Werner Heisenberg became prepared for a discovery that would change the course of human thought. He learned, long before formalizing it mathematically, that uncertainty is not simply a problem to be solved. It is a condition to be understood, and it was this understanding, rooted deeply in his early experiences, that would eventually lead him to reveal one of the most profound truths ever uncovered about the nature of the universe. The revolutionary idea that would define Werner Heisenberg's place in history did not arrive as a sudden flash of inspiration detached from struggle. It emerged slowly, painfully, and almost reluctantly, forged through intellectual frustration, physical exhaustion, and a deep confrontation with the limits of existing knowledge. By the early 1920s, quantum theory was already a patchwork of partial successes and conceptual failures. Physicists had tools that worked mathematically, but no coherent picture of what was truly happening inside the atom. The field was advancing, yet no one felt secure about its foundations. It was within this unstable landscape that Heisenberg began to rethink not just specific equations, but the very purpose and method of theoretical physics. At that time, atomic theory relied heavily on hybrid models that mixed classical mechanics with ad hoc quantum rules. These models produced correct numerical results in some cases, but they lacked internal consistency. Electrons were treated as particles following orbits, yet were forbidden from behaving according to classical laws while in those orbits. Energy changes occurred in sudden jumps without explanation. To many physicists, this was intellectually unsatisfying but tolerable, a temporary compromise until a deeper theory could be found. For Heisenberg, however, this compromise felt dishonest. He sensed that the confusion stemmed from trying to force nature into concepts it no longer fit. Heisenberg became increasingly convinced that visual representations were misleading. Diagrams of electrons circling nuclei offered comfort, but they were built on assumptions that could not be tested. No experiment could directly observe an electron's path inside an atom. These imagined trajectories were metaphors, not measurements. Heisenberg began to question why physics should rely on quantities that could never, even in principle, be observed. This question struck at the heart of classical thinking, which assumed that all physical properties existed independently of observation. The more Heisenberg reflected on this issue, the more radical his thoughts became. He started to suspect that the crisis in quantum theory was not due to insufficient mathematics, but due to the wrong questions being asked. Instead of asking what electrons are doing, perhaps physicists should ask what can actually be known about electrons. This shift might seem subtle, but it represented a profound philosophical break. It meant redefining physics not as a description of objective reality, as it is, but as a framework for organizing observable phenomena. This intellectual struggle intensified during Heisenberg's collaborations with other leading physicists. Conversations with Niels Bohr, in particular, were both inspiring and exhausting. Bohr emphasized the limits of classical language and argued that quantum phenomena required entirely new modes of description. While Heisenberg admired Bohr deeply, he also felt unsatisfied by explanations that relied heavily on verbal philosophy without providing a clear mathematical structure. Heisenberg wanted a theory that was precise, predictive, and internally consistent, even if it abandoned intuitive imagery altogether. The decisive moment came in 1925 during a period of isolation that would become legendary. Suffering from severe hay fever, Heisenberg retreated to the island of Helgoland in the North Sea to escape allergens and focus on his work. Cut off from distractions, physically weakened, and mentally strained, he immersed himself in the problem that had been haunting him for months. The question was simple in appearance, but devastating in implication. How could one construct a theory of atomic behavior using only observable quantities? Heisenberg began by examining atomic spectra, the discrete lines of light emitted or absorbed by atoms. These spectral lines were among the most reliable experimental data available. They corresponded to transitions between energy levels, not to continuous motion. Instead of describing electrons moving through space, Heisenberg focused on these transitions themselves. He treated them as the fundamental elements of the theory, rather than as secondary effects of hidden motions. This approach required abandoning the classical idea of continuous trajectories. In its place, Heisenberg introduced mathematical objects that encoded relationships between observable quantities, such as frequencies and intensities of spectral lines. These objects did not behave like ordinary numbers. When multiplied, the order of multiplication mattered, a shocking departure from conventional arithmetic. At first, Heisenberg did not fully understand the mathematical structure he had created. He knew only that it produced correct results and that it avoided unobservable concepts. When Max Born later recognized that Heisenberg's calculations corresponded to a new form of matrix mathematics, the revolutionary nature of the work became clearer. This new framework, later called matrix mechanics, was abstract, non-visual, and deeply counterintuitive. It offered no picture of electrons moving along paths. Instead, it described a network of possible transitions, governed by probabilities and mathematical relationships. Reality at the atomic level, according to this theory, could not be pictured in space and time in the classical sense. The emotional impact of this breakthrough on Heisenberg was intense. He reportedly worked through the night, and at dawn climbed a rock to watch the sun rise, overwhelmed by the realization that he had found something fundamentally new. Yet even in this moment of triumph, there was uncertainty. Heisenberg was not sure how his ideas would be received. He knew they challenged deeply rooted assumptions and required abandoning cherished intuitions. The excitement of discovery was inseparable from anxiety. What made Heisenberg's idea truly revolutionary was not just its mathematical novelty, but its philosophical implications. By constructing a theory based solely on observables, he implicitly rejected the notion that physics must describe an underlying reality independent of measurement. Instead, he suggested that the structure of physical theory reflects the conditions under which knowledge is obtained. This was a radical departure from centuries of scientific thought. The theory also revealed an unexpected feature of nature, non-commutativity. The fact that certain quantities did not commute mathematically hinted at deeper constraints on what could be known simultaneously. Although Heisenberg had not yet formulated the uncertainty principle explicitly, the seeds were already present. The mathematics itself was telling a story about limits, about the impossibility of assigning precise values to all properties at once. Reactions to Heisenberg's work were mixed. Some physicists were excited by its success in explaining experimental data. Others were deeply unsettled by its abstraction and lack of intuitive clarity. Even those who recognized its power struggled to understand what it meant. The theory worked, but it did not explain in familiar terms. This tension between predictive success and conceptual discomfort became a defining feature of quantum mechanics. Heisenberg himself was keenly aware of this tension. He did not claim to have uncovered the ultimate truth about reality. Instead, he emphasized that his theory provided a consistent way to relate observations. For him, this was enough. He believed that demanding more, such as a classical picture of atomic processes, was not only unnecessary but misleading. Physics, he argued, should adapt its concepts to nature, not force nature to conform to human expectations. The birth of this revolutionary idea marked a turning point not only in Heisenberg's career, but in the history of science. It demonstrated that progress sometimes requires letting go of deeply ingrained assumptions. The belief that every physical process must be visualizable, deterministic, and continuous had to be abandoned. In its place emerged a new vision of reality, one that was relational, probabilistic, and constrained by fundamental limits. This transformation did not occur in isolation. It was the culmination of decades of experimental anomalies, theoretical frustrations, and philosophical questioning. Yet Heisenberg's contribution was unique in its boldness and clarity. He did not try to repair classical physics. He replaced it with something entirely different. By doing so, he made certainty itself a subject of scientific inquiry. The revolutionary idea born during this period was not merely a technical achievement. It was a statement about the nature of knowledge. It suggested that the universe does not yield its secrets easily, and that understanding it requires humility as well as intelligence. The atomic world, Heisenberg showed, does not obey the rules of everyday experience. It demands new ways of thinking, new forms of mathematics, and new philosophical attitudes. In the end, the birth of Heisenberg's revolutionary idea revealed something profound: that the limits of human knowledge are not obstacles imposed by ignorance alone, but features woven into the fabric of reality. This realization would soon be crystallized in one of the most famous principles in science. But even before it was named, the essence of that principle was already present in Heisenberg's work. Certainty, once taken for granted, had been quietly and irrevocably undermined. As the implications of this new framework began to sink in, it became clear that Heisenberg had done more than solve a technical problem. He had altered the direction of theoretical physics by redefining what it meant to explain nature. His work suggested that explanation no longer required a mechanical picture unfolding in space and time, but rather a coherent mathematical structure that connected observations. This was a difficult shift for many physicists to accept, because it challenged the very criteria by which theories had long been judged. One of the most unsettling aspects of Heisenberg's approach was its silence about what particles were really doing when not being observed. Classical physics had always assumed that objects possessed definite properties at all times. Even when those properties were unknown, they were believed to exist. Heisenberg's formulation quietly removed this assumption. In his framework, physical quantities did not have definite values independent of measurement. They existed only within the context of interactions and observations. This idea, though not yet fully articulated in philosophical terms, represented a profound break from the past. As colleagues studied the new mathematics more closely, they noticed its strange internal logic. Quantities that represented familiar concepts such as position and momentum behaved in unexpected ways. The order in which calculations were performed mattered, leading to different results. This was not a mathematical accident. It was a reflection of the underlying structure of the theory. The equations themselves encoded a limit on what could be simultaneously defined. In effect, the mathematics was expressing a physical truth that intuition alone could not grasp. Heisenberg initially struggled to explain what this meant conceptually. He was aware that the theory worked, but he was cautious about attaching interpretations that went beyond its formal success. This restraint was characteristic of him. He believed that physics should not claim more than it could justify experimentally. Where classical physicists had confidently described the invisible mechanisms behind phenomena, Heisenberg preferred to remain silent rather than speculate. This intellectual humility would later become one of his defining traits. The response from the broader scientific community was intense and divided. Younger physicists, already accustomed to the instability of the field, were often more receptive. They saw in Heisenberg's work a path forward, a way to escape the contradictions that had plagued atomic theory. Older physicists, trained in the traditions of classical mechanics, found the new approach deeply unsettling. Some rejected it outright, arguing that a theory without a clear picture of reality was incomplete or even meaningless. Debate soon extended beyond mathematics into philosophy. What was the goal of physics? Was it to describe reality as it truly is, or merely to predict the outcomes of experiments? Heisenberg's work seemed to support the latter view, at least at the atomic scale. This raised uncomfortable questions about objectivity, realism, and the role of the observer. If physical properties depended on measurement, then the observer could no longer be considered separate from the system being studied. Heisenberg did not claim that reality was subjective or arbitrary. He believed firmly in the existence of an external world governed by laws, but he argued that the structure of those laws limited the kind of knowledge humans could obtain. The observer was not creating reality, but interacting with it in ways that imposed constraints. This distinction was subtle but crucial. It allowed Heisenberg to avoid both naive realism and radical subjectivism. As discussions intensified, Heisenberg's ideas began to influence the development of other formulations of quantum mechanics. Erwin Schrödinger introduced wave mechanics, which offered a different mathematical approach and seemed, at first, more intuitive. Schrödinger's waves provided visual appeal, something Heisenberg's matrices lacked. Yet deeper analysis revealed that the two formulations were mathematically equivalent. They described the same physical reality from different perspectives. This equivalence reinforced the sense that quantum theory was not about pictures, but about abstract relationships. For Heisenberg, this convergence was both reassuring and revealing. It suggested that no single representation could capture the full essence of quantum phenomena. Different mathematical languages could describe the same underlying structure, each highlighting certain aspects while obscuring others. This insight further weakened the classical demand for a single, definitive picture of reality. Instead, physics began to resemble a set of complementary descriptions, each valid within its domain. The revolutionary idea also forced a re-examination of causality. In classical physics, causes produced effects in a straightforward, predictable manner. In the new quantum framework, events could be described only in terms of probabilities. Even with complete knowledge of a system's current state, future outcomes could not be predicted with certainty. This did not mean that anything could happen, but that nature imposed intrinsic limits on predictability. For many, this was the most disturbing implication of all. Heisenberg himself grappled with these consequences. He was not indifferent to the philosophical weight of his work. On the contrary, he took it seriously and reflected deeply on its meaning. Yet he resisted turning physics into metaphysics. He believed that scientific concepts must remain closely tied to experimental practice. When discussions drifted too far into speculation, he often redirected attention back to what could be measured and tested. This pragmatic stance did not diminish the radical nature of his contribution. By grounding theory in observables, Heisenberg had shifted the foundation of physics. The success of his approach demonstrated that abandoning classical intuitions did not weaken science, it strengthened it. Predictions became more accurate, and previously inexplicable phenomena found coherent explanations. The price was the loss of certainty, but the reward was a deeper, more honest understanding of nature. As the months passed, it became clear that Heisenberg's work marked the beginning of a new era. Quantum mechanics was no longer a collection of provisional rules. It was becoming a unified theory with its own internal logic and principles. The birth of this theory was not a smooth transition but a rupture, a moment when the continuity of scientific tradition was broken and reassembled in a new form. Heisenberg's personal experience of this transformation was complex. He was proud of his achievement, yet keenly aware of its incompleteness. He knew that many questions remained unanswered, particularly regarding interpretation. His theory described how measurements were related, but it did not fully explain what measurement itself meant. These unresolved issues would occupy physicists and philosophers for decades to come. Despite these uncertainties, one conclusion was unavoidable. The old dream of complete certainty, inherited from classical physics, could no longer be sustained. Heisenberg's revolutionary idea had exposed a fundamental feature of the natural world, that there are limits to what can be known, not because of technological shortcomings, but because of the structure of reality itself. Knowledge was no longer a matter of simply uncovering hidden facts. It was shaped by the conditions under which those facts were accessible. This realization altered the self-image of science. Physics was no longer the quest for a perfectly detailed map of the universe. It became an exploration of relationships, constraints, and possibilities. The role of theory shifted from depicting reality to organizing experience in the most consistent and predictive way possible. In this sense, Heisenberg's contribution was as much about epistemology as it was about physics. The birth of this revolutionary idea also had a human dimension. It demonstrated the power of intellectual courage. Heisenberg dared to trust the implications of his mathematics even when they contradicted common sense and tradition. He accepted confusion as a temporary companion and uncertainty as a guide rather than an enemy. This attitude would become emblematic of the quantum era. In retrospect, it is clear that this period marked a decisive break with the past. The classical world, governed by certainty and determinism, gave way to a quantum world defined by probability and limits. Heisenberg did not cause this shift alone, but his work crystallized it in a form that could not be ignored. By reimagining the foundations of physics, he revealed that certainty itself was not a universal principle, but a special case applicable only within certain boundaries. The revolutionary idea born from Heisenberg's struggle thus reshaped not only physics, but humanity's understanding of knowledge. It taught that the deepest truths of nature might resist complete articulation, and that scientific progress sometimes involves learning how not to ask certain questions. In making certainty impossible, Heisenberg did not diminish science. He gave it a new kind of honesty, one that acknowledged both the power and the limits of human understanding. The collapse of certainty at the quantum level did not happen because scientists suddenly lost precision or because experiments became unreliable. It happened because nature itself revealed a structure that could not be described using the assumptions that had governed physics for centuries. At the smallest scales of reality, the very ideas of definite position, exact motion, and predictable outcomes began to dissolve. What emerged was not chaos, but a different kind of order, one in which limits to knowledge were built into the fabric of the universe. At the quantum level, particles such as electrons do not behave like solid objects moving along clear paths. When scientists tried to observe them, they found behavior that defied classical expectations. Electrons sometimes appeared localized, like particles, and at other times spread out, like waves. This was not a flaw in observation, but a genuine feature of how these entities exist. The properties that seemed natural and obvious in everyday life no longer applied. The closer scientists looked, the stranger reality became. One of the main reasons certainty collapsed was the unavoidable interaction between the observer and the observed. In classical physics, it was assumed that measurements could be made without significantly disturbing the system. At the quantum level, this assumption fails completely. To observe a particle, one must interact with it, often by using light or other particles. These interactions are not gentle. They change the state of what is being measured. As a result, the act of observation becomes part of the phenomenon itself. There is no way to separate the system from the measurement process. This led to a radical realization. Properties such as position and momentum cannot both have exact values at the same time. The more precisely one is defined, the more the other becomes uncertain. This is not due to poor instruments or human error. It is a fundamental limitation imposed by nature. The quantum world does not allow all properties to be sharply defined simultaneously. Certainty collapses not because we fail to measure correctly, but because the universe does not permit complete definition. Another reason for the collapse of certainty lies in the probabilistic nature of quantum events. In classical physics, probability was a practical tool used when systems were too complex to track in detail. In quantum physics, probability is fundamental. Even when all possible information about a system is known, the outcome of a measurement can only be predicted in terms of likelihood, not certainty. The universe, at its most basic level, does not guarantee specific outcomes. It only provides probabilities. This was deeply unsettling because it challenged the principle of determinism. For centuries, science had been built on the idea that the present determines the future with absolute necessity. At the quantum level, this principle breaks down. Identical experiments performed under identical conditions can produce different outcomes. The laws of physics still operate, but they govern distributions of results rather than single, definite events. Nature follows rules, but those rules do not eliminate uncertainty. The collapse of certainty was also driven by the failure of classical concepts to describe quantum reality. Ideas such as trajectory, orbit, and exact location are rooted in everyday experience. They assume objects exist in space and time in well-defined ways. Quantum entities do not conform to these assumptions. They are better described as possibilities rather than objects, as patterns of probability rather than solid things. When scientists tried to force classical language onto quantum phenomena, contradictions arose. The problem was not the phenomena, but the language used to describe them. Mathematics played a crucial role in revealing this collapse. Quantum equations did not behave like classical ones. Certain quantities could not be exchanged freely without changing results. This mathematical structure reflected a physical truth. Some aspects of reality are incompatible in the sense that defining one precisely prevents the precise definition of another. The equations were not just abstract symbols, they encoded the limits of what can be known. Certainty was not lost by interpretation alone, it was mathematically forbidden. The collapse of certainty also affected the concept of reality itself. Classical physics assumed that physical properties existed whether or not they were observed. Quantum physics challenges this assumption. At the quantum level, properties become definite only when measured. Before measurement, systems are described by a range of possible outcomes. This does not mean reality is imaginary or subjective, but it does mean that reality is not fully defined independent of interaction. What exists is not a single outcome, but a set of potentialities. This idea forced a rethinking of objectivity. Objectivity in classical science meant describing the world as it is, independent of observers. In quantum physics, objectivity shifts toward describing what can be said about the world given specific experimental arrangements. Different setups reveal different aspects of the same system. No single experiment can capture all properties at once. Certainty collapses because completeness becomes impossible. Knowledge is always partial, conditioned by how questions are asked. Importantly, the collapse of certainty does not imply that the universe is irrational or random in a meaningless sense. Quantum laws are precise and reliable. They allow accurate predictions of statistical outcomes and have been confirmed by countless experiments. Technologies such as semiconductors, lasers, and modern electronics rely on these laws. What collapsed was not order, but the classical expectation of total predictability and complete description. This transformation had profound philosophical consequences. It suggested that human knowledge has inherent limits, not because humans are flawed, but because reality itself imposes boundaries. The dream of total control and perfect foresight had to be abandoned. Science was no longer the path to absolute certainty, but to the best possible understanding within defined limits. This required humility, a recognition that nature does not conform to human intuition. The collapse of certainty at the quantum level marked a turning point in the history of thought. It showed that progress does not always mean greater control or clearer images. Sometimes progress means learning where clarity ends and ambiguity begins. Quantum physics revealed that uncertainty is not an obstacle to knowledge, but a fundamental feature of existence. By confronting this truth, science did not weaken. It became more honest, more accurate, and more aligned with the true structure of reality. In revealing why certainty collapses, the quantum world teaches a deeper lesson. It reminds us that reality is richer and stranger than our everyday experience suggests. The universe is not a rigid machine running on predictable tracks. It is a dynamic interplay of possibilities, governed by laws that allow precision without guaranteeing certainty. This insight reshaped physics and forever changed how humanity understands the nature of knowledge itself. The uncertainty principle stands as one of the most misunderstood ideas in modern science, not because it is vague, but because it challenges deeply rooted assumptions about knowledge and control. At first glance, it seems to suggest that scientists simply lack the tools to measure the world accurately. In reality, it says something far more profound. It reveals that there are fundamental limits to what can be known about nature, limits that no improvement in technology can overcome. This principle does not describe human failure, it describes how the universe itself is structured. At its core, the uncertainty principle states that certain pairs of physical properties are linked in such a way that increasing the precision of one inevitably reduces the precision of the other. The most famous example involves position and momentum. The more precisely a particle's position is known, the less precisely its momentum can be determined, and vice versa. This is not a technical inconvenience or an experimental flaw. It is a direct consequence of the wave, like nature of matter at the quantum level. To understand the true meaning of this principle, it is important to abandon classical intuition. In everyday life, objects have definite positions and velocities at all times. A car traveling down a road occupies a specific place and moves with a measurable speed. Quantum particles do not behave this way. They are described by wave functions that spread out over space, representing a range of possible positions and momenta. These waves are not physical ripples in space, but mathematical descriptions of probability. When a measurement is made, this range of possibilities narrows. Measuring position forces the wave function to become localized, which automatically spreads out the range of possible momenta. Measuring momentum does the opposite. This trade-off is built into the mathematics of quantum theory. It arises from the fundamental structure of the equations, not from the limitations of measuring devices. Even in a perfect experiment with ideal instruments, the uncertainty remains. The principle also reveals that measurement is an active process, not a passive one. To measure something at the quantum level, interaction is required. This interaction changes the system in unavoidable ways. The idea that one can observe without influencing no longer applies. The observer is not separate from the phenomenon, but part of it. This does not mean that reality is subjective, but it does mean that knowledge is relational. What can be known depends on how one chooses to measure. A common misunderstanding is that the uncertainty principle implies randomness or chaos without order. This is not the case. The principle places precise mathematical limits on uncertainty. It does not say that anything can happen, but that outcomes are constrained within well-defined boundaries. Quantum mechanics remains one of the most accurate theories ever developed, capable of predicting experimental results with astonishing precision. Uncertainty does not weaken the theory, it defines its scope. Another important aspect of the principle is that it applies universally, not just to exotic laboratory experiments. All matter is subject to quantum laws. The reason uncertainty is not noticeable in everyday life is that the effects become significant only at very small scales. For large objects composed of enormous numbers of particles, uncertainties average out and become negligible. Classical certainty emerges as an approximation, not as a fundamental truth. The uncertainty principle also reshaped the meaning of causality. In classical physics, knowing the present state of a system allows exact prediction of its future. In quantum physics, even complete knowledge of a system's wave function allows only probabilistic predictions. The laws of physics still govern how systems evolve, but they govern probabilities rather than certainties. The future is constrained, but not predetermined in a single, unavoidable way. This shift had deep philosophical implications. It forced scientists to reconsider the goal of explanation. Instead of asking for exact trajectories and definite outcomes, quantum physics asks for probability distributions and expectation values. The focus moves from certainty to consistency, from absolute prediction to reliable statistical description. This does not represent a retreat from knowledge, but a refinement of what knowledge means. The uncertainty principle also clarified a crucial point about the nature of reality. It showed that some properties do not exist independently of the context in which they are measured. Position and momentum are not hidden values waiting to be revealed, they are defined through measurement interactions. This challenges the classical idea of an objective reality fully defined at all times. Instead, reality at the quantum level is characterized by potentialities that become actual under specific conditions. Despite its abstract nature, the uncertainty principle has very practical consequences. Modern technologies depend on it. The stability of atoms, the behavior of electrons in solids, and the functioning of electronic devices all rely on quantum principles. Without uncertainty, atoms would collapse, chemistry would not exist, and the material world as we know it would be impossible. What appears as a limitation is actually a condition for the existence of structure and complexity. The principle also invites a more humble view of human knowledge. It suggests that there are boundaries beyond which questions lose meaning. Asking for exact position and exact momentum simultaneously is not a difficult problem, it is an ill-defined question. Quantum physics teaches that not all questions that can be imagined can be answered by nature. Understanding involves learning which questions are meaningful and which are not. Importantly, the uncertainty principle does not imply that the universe is irrational or mysterious beyond comprehension. It provides a clear, testable statement about the limits of precision. Its predictions have been confirmed repeatedly, and no experiment has ever violated it. It stands not as a symbol of confusion, but as a cornerstone of clarity about what can and cannot be known. In the end, the true meaning of the uncertainty principle lies in its redefinition of certainty itself. It tells us that certainty is not the natural state of the universe, but an approximation that emerges under certain conditions. At the deepest level, reality is governed by relationships, probabilities, and limits. By revealing these limits, the principle does not close the door to understanding. It opens a new one, where knowledge is defined not by absolute control, but by faithful description of how nature truly behaves. The impact of Werner Heisenberg's ideas extended far beyond equations and laboratories, reaching into philosophy, ethics, and the question of responsibility in a world transformed by scientific power. As quantum mechanics reshaped the understanding of nature, it also forced a reconsideration of humanity's role as an observer, a knower, and an actor within that nature. Science was no longer a detached mirror reflecting an objective world, it became an active participant in shaping how reality is encountered and understood. This shift carried profound consequences for how knowledge, truth, and responsibility were conceived. One of the most significant philosophical consequences of Heisenberg's work was the challenge it posed to traditional realism. Classical science assumed that the world existed with well-defined properties independent of observation. Quantum mechanics disrupted this assumption by showing that certain properties only become definite through interaction. This did not deny the existence of an external reality, but it redefined what could meaningfully be said about it. Reality, at the quantum level, was no longer a collection of fixed attributes, but a network of relationships revealed through measurement. This realization altered the meaning of objectivity. Objectivity could no longer mean describing a world entirely independent of observers. Instead, it meant providing consistent and communicable accounts of experimental results under specified conditions. Knowledge became contextual without becoming subjective. Heisenberg emphasized that science remains objective because its results are reproducible and shared, even though they depend on experimental arrangements. This subtle distinction helped preserve the integrity of science while acknowledging its limits. The philosophical implications extended into epistemology, the study of knowledge itself. Heisenberg's work suggested that knowledge is not a passive reflection of reality, but an interaction between the knower and the known. The questions asked, the tools used, and the conditions imposed all shape what can be discovered. This view resonated with broader philosophical movements that emphasize the active role of the human mind in structuring experience. Quantum mechanics provided a scientific foundation for ideas that had previously belonged mainly to philosophy. Beyond philosophy, Heisenberg's career raised urgent ethical questions. The same scientific advances that revealed the structure of the atom also enabled unprecedented destructive power. During the Second World War, nuclear research became a central focus of military efforts. Heisenberg, who remained in Germany during this period, found himself at the intersection of science and politics. His involvement in nuclear research has been the subject of intense debate and controversy, reflecting the moral complexity of scientific responsibility in times of conflict. What is clear is that Heisenberg was deeply aware of the ethical dimension of science. He understood that scientific knowledge does not exist in isolation from society. Discoveries change the world, and those who make them cannot entirely escape responsibility for how they are used. Yet he also recognized that scientists do not control political decisions. This tension between responsibility and power is one of the enduring ethical dilemmas of modern science, brought into sharp focus by the atomic age. Heisenberg's reflections after the war reveal a man grappling with these issues. He spoke openly about the limits of scientific authority and the dangers of viewing science as morally neutral. He argued that scientists must remain conscious of the broader consequences of their work, even when those consequences extend beyond their immediate control. At the same time, he resisted the idea that scientific inquiry should be constrained by fear. For him, the solution lay not in abandoning science, but in integrating it more thoughtfully into human culture and ethical reflection. The philosophical lessons of quantum mechanics also encouraged humility. If nature itself imposes limits on what can be known, then claims of absolute certainty become suspect not only in science, but in other domains as well. Heisenberg often emphasized that the abandonment of certainty in physics could serve as a model for intellectual modesty in philosophy, politics, and religion. Recognizing limits, he believed, was a sign of maturity rather than weakness. This humility did not imply relativism. Heisenberg rejected the notion that all interpretations were equally valid or that truth was merely a matter of perspective. Quantum mechanics, despite its limits, provides precise and reliable knowledge. The lesson was not that truth is inaccessible, but that it is structured and constrained. Understanding grows through dialogue between theory and experiment, not through claims of final answers. Heisenberg also explored the relationship between science and language. He argued that classical language evolved to describe everyday experiences, and therefore struggles to capture quantum phenomena accurately. This insight had philosophical significance, highlighting how human concepts shape understanding. Scientific progress, in his view, often requires the creation of new conceptual frameworks rather than the refinement of old ones. Language, like theory, must adapt to reality rather than dictate it. In discussing responsibility, Heisenberg emphasized education and cultural integration. He believed that scientific knowledge should not be isolated within technical communities, but shared and discussed within society as a whole. Only through understanding could democratic societies make informed decisions about the use of scientific power. This belief reflected his broader commitment to bridging the gap between science and the humanities, a commitment rooted in his own classical education. The legacy of Heisenberg's ideas thus includes a vision of science as a human activity embedded within ethical and philosophical contexts. Quantum mechanics did not simply change equations, it changed attitudes toward knowledge and power. It revealed that scientific understanding comes with obligations as well as insights. The scientist is not merely a discoverer of facts, but a participant in shaping the future. In the modern world, where technology influences nearly every aspect of life, these lessons remain urgently relevant. The uncertainty revealed by quantum physics serves as a reminder that control is never absolute and that wisdom must accompany knowledge. Heisenberg's work encourages a balanced view of science, one that celebrates its achievements while acknowledging its limits and responsibilities. Ultimately, the connection between science, philosophy, and responsibility formed a central theme in Heisenberg's later reflections. He saw quantum mechanics not as a threat to rationality, but as an expansion of it. By accepting uncertainty, science gained depth and honesty. By recognizing responsibility, it gained moral significance. Together, these insights shaped a legacy that reaches far beyond physics, offering guidance for how humanity might navigate a world increasingly shaped by its own discoveries. Werner Heisenberg's legacy is not confined to a single principle or a narrow chapter in the history of physics. It extends across science, technology, philosophy, and the way modern humanity understands reality itself. By demonstrating that certainty has limits, Heisenberg transformed the goals of scientific inquiry and reshaped the intellectual landscape of the 20th century. His influence continues to shape how knowledge is produced, interpreted, and applied long after the debates of his own time have faded. One of the most enduring aspects of Heisenberg's legacy is the transformation of physics from a search for exact descriptions to a study of relationships and constraints. Classical physics aimed to provide a complete account of nature, specifying exact values for all properties at all times. Quantum mechanics replaced this vision with a framework that focuses on probabilities, interactions, and limits. This shift did not weaken physics, it made it more accurate and more honest. Modern physics no longer promises certainty where none is possible. Instead, it offers reliable predictions within clearly defined boundaries. Technologically, Heisenberg's ideas helped lay the foundation for the modern world. Quantum mechanics underpins much of today's technology, from transistors and integrated circuits to lasers and medical imaging devices. These applications do not rely on overcoming uncertainty, but on understanding and using it. The stability of atoms, the behavior of electrons in materials, and the flow of energy at microscopic scales all depend on quantum principles. In this sense, uncertainty is not an obstacle to progress, but a resource that makes complex technology possible. Heisenberg's legacy also extends deeply into philosophy. His work challenged long-standing assumptions about objectivity, realism, and causality. Philosophers were forced to reconsider what it means for something to be real if its properties are not fully defined independent of observation. This did not lead to the abandonment of realism, but to more nuanced forms of it, acknowledging that knowledge is shaped by interaction. The dialogue between physics and philosophy that quantum mechanics stimulated remains active today, influencing debates about consciousness, information, and the nature of time. In education, Heisenberg's influence reshaped how science is taught and understood. Students now learn that scientific theories are not final truths, but models with specific domains of validity. This perspective encourages critical thinking and adaptability. It teaches that progress often involves recognizing the limits of existing frameworks and developing new ones. Heisenberg's work serves as a powerful example of how questioning foundational assumptions can lead to deeper understanding rather than confusion. Culturally, the idea that certainty is impossible at a fundamental level has resonated far beyond science. It has influenced literature, art, and broader intellectual movements that emphasize ambiguity, complexity, and plurality of perspectives. While quantum mechanics does not justify philosophical relativism, it has contributed to a cultural shift away from rigid, absolutist thinking. The recognition that limits exist has encouraged more flexible and reflective approaches to knowledge. Heisenberg himself played an important role in shaping this broader legacy through his writings and public engagement. He did not retreat into technical specialization, but spoke openly about the meaning of scientific discoveries. He emphasized that science and the humanities should not be isolated from each other. Understanding the world, he argued, requires both precise measurement and thoughtful interpretation. This integrative vision remains relevant in an age where scientific expertise often seems disconnected from ethical and cultural considerations. Another key aspect of Heisenberg's legacy is the model he provided for intellectual courage. He demonstrated that it is possible to challenge deeply entrenched ideas without rejecting rigor or discipline. His willingness to abandon familiar concepts in favor of abstract mathematics showed that creativity and precision are not opposites, but partners. This example continues to inspire scientists who work at the frontiers of knowledge, where intuition often fails and new conceptual tools are required. Heisenberg's work also left an enduring mark on the philosophy of science itself. It reinforced the idea that scientific theories are not mirrors of reality, but structured ways of organizing experience. This insight has shaped how scientists and philosophers think about explanation, prediction, and understanding. The success of quantum mechanics suggests that a theory can be profoundly useful even if it challenges common sense. Truth in science, Heisenberg's legacy suggests, is measured by coherence, consistency, and empirical success, not by intuitive comfort. In the broader historical context, Heisenberg's legacy is inseparable from the moral lessons of the 20th century. The same scientific advances that expanded knowledge also increased humanity's capacity for destruction. Heisenberg's life and work highlight the dual nature of scientific power. His reflections on responsibility remind us that scientific progress must be accompanied by ethical awareness. This lesson remains urgent in a world facing challenges such as artificial intelligence, biotechnology, and climate change. Perhaps the most profound element of Heisenberg's legacy lies in how it reshaped humanity's self-understanding. By revealing limits to knowledge, quantum mechanics challenged the idea that humans could achieve total mastery over nature. This was not a defeat, but a maturation. It suggested that wisdom involves recognizing boundaries as well as possibilities. In this sense, Heisenberg's contribution helped move science from an era of conquest to an era of dialogue with nature. The idea that certainty is impossible has also influenced how uncertainty itself is valued. Instead of being seen purely as a problem, uncertainty is now recognized as a source of creativity and discovery. It opens space for new questions and new approaches. Heisenberg's work shows that accepting uncertainty can lead to deeper insight, not paralysis. This lesson applies not only to science, but to decision-making and understanding in many areas of life. Today, nearly a century after Heisenberg's most important discoveries, their relevance has not diminished. Quantum mechanics continues to be tested, refined, and applied in new contexts, yet its core principles remain intact. The limits revealed by the uncertainty principle have never been violated. This endurance testifies to the depth of Heisenberg's insight. He did not offer a temporary fix, but a fundamental reorientation of thought. In the end, Werner Heisenberg's legacy is not simply that he made certainty impossible. It is that he showed how knowledge can thrive without certainty. He demonstrated that understanding does not require absolute answers, only honest ones. By embracing limits, science gained a richer and more accurate picture of reality. Through this transformation, Heisenberg left humanity with a lasting gift, a way of thinking that balances precision with humility, power with responsibility, and curiosity with respect for the mystery at the heart of existence.